Greetings, welcome. A couple of videos ago, we saw some strange behavior with the pulse motor in the penny roll 3 video, and that was when we added pennies in and increased the mass, approximately doubled the mass of the rotor. The rotor spun faster. It went faster, and it went faster whether under load or not under load. Now, someone in the comments said you need to put an amp meter on there, and he's right. I was eyeballing the amps on the power supply, but maybe in the back of my mind I was giving myself a way out as well. But I will put an amp meter on for the next video when I do this again, and I'll tell you what we're going to see is not only will the amp draw not increase, it will probably decrease a very small amount because you're going to have shorter pulses and you're going to be hitting more of the reactive resistance. That's just the way magnetic motors work. Even like Tesla cars, they're going to have less torque as they go faster, whereas internal combustion engines, until they want to fly apart, they hit the power zone at like 4,000 RPMs or something, so they generally have more torque as they go faster. It's neither here nor there. So it was kind of a really surprising finding because the resistance that was added to slow it down was a generator coil that was shorted, and so I'll just leave it there. And I was thinking, how can this be? Again, I need to do more of it, but I kind of think I know what I'm going to see. It's like, did I somehow hit a sweet spot where I'm like decreasing, I don't know. It was like, but, like I was trying to think of, is it decreasing resistance with adding the mass, and if I add a little more mass, it's going to increase resistance. I don't think that's what's going on. And again, it's just because you can think back to real life experience. And I gave the two examples of empty or a full Ferris wheel that you push, or an empty or a full swing that you push. So then I was also thinking in the back of my mind, does it have something to do with angular momentum? Because that presents its own questions. And I thought about it, it's like, no, because you can think of a linear example. Suppose you're at on a toy railroad, and there's a little rail cart on there that you can push, and you push it when it's empty, and it goes through a bunch of branches and brambles, and it comes to a stop. And now you fill it with apples. You push it with the same push, and it's going to go through the apples. I mean, you just kind of know that from being alive and in the world. But it's like, wait a minute, how is this Newtonian? Because, I guess there's some, I'm not going to go there. I'll just say that you don't want to find yourself in a quarrel with Isaac, right? I remember reading, I don't know if it was in a book or somewhere about him, that I think it was like some leading French scientist sent out a problem to all the leading scientists of Europe, and I can't remember, something about the movement of the stars in the heavens or some kind of physics problem, and he gave them all a year to see if anyone could answer it. And 2 weeks later, someone that no one had ever heard of gave the answer. And so everyone was like, who is this guy? And the person who sent it out said, the lion is known by his claw. So it's like, this has got to be Newton. And of course it was. He had submitted the answer under a nom de plume. All that is just to say, I mean, you don't want to get in an argument with Newton. And his laws of motion are pretty well established, let's say. So how could this be, and how does it fit? And so I thought about it more, and I thought, yeah, all right, I think I get it now. But I wanted to try to illustrate what I'm talking about, and I thought, well, can I find just a, not not some like circuit simulator, just a physics simulator. And this is a really simple one. I'll show you another page that I found that has a bunch of cool stuff on it. But this is a really simple one, and this is exactly, you know, what I needed to see. So I guess it's out of University of Colorado, and we can just go with the intro version. So I wanted to find one that did resistance. It's actually having a lot of difficulty finding a plain old physics simulator that models resistance. I'm sure they're there. It just, in 10-15 minutes, I didn't find a good one. But you can think about what is resistance. Resistance is something running into something else. And I don't want to go there. Most people, I think, would say that even when the resistance is magnetic fields, it's probably things running into each other. But in any event, we can consider resistance as two things running into each other. And then the question becomes, is it an elastic collision or an inelastic collision? So in other words, if you have that cart going through the branches, is that closer to an elastic or an inelastic? And because the branches don't stick to the cart, I'd call it an elastic collision. So here, let's make the two balls the same mass to start with, and then you can change the velocity by moving this back and forth. So if we do it like this, just real quick, and that one's going fast. Let's make this one stationary. What happens when a ball of equal mass, and you know, if you've ever played billiards, you kind of have an idea, runs into this one, and it does that, and it comes to a halt. What if we make this ball much smaller than the other, like the 90-pound weakling hitting Arnold Schwarzenegger or Hulk Hogan? What's going to happen then? It doesn't just come to a stop. He bounces off and starts going the other way. You know, I guess I never watched one of Hulk Hogan's shows. But I guess after he died, I read he had a saying: pray, exercise, and take your vitamins. And I thought about it, and I was like, that's really good advice. It's like profound. Really good advice. So what if we change the velocity? Now we're going to throw this really quickly at here, at Hulk Hogan, and it just bounces off more quickly and goes the other direction more quickly. So what about now if we change this around and we say that this has a lot of mass, say 3, and we'll leave the other one at 1.5. So now this is where you've increased the mass on the rotor. Now it's still moving in the right direction. And we can't increase that past 3, but we can make the other one much smaller, 0.25. And no, it doesn't like that. 0.2. That's okay. So in other words, this is the mass in relationship to the resistance. And so now this mass is much larger. And the thing to keep an eye on when we do this is, here's your initial velocity, and you know they change it after the collision. So here's what you see. You can barely even notice that that's shorter. But we just saw if they were equal, then the first one comes to a stop. Now if they're near equal, so we'll make this 2 instead of 0.2. No, it didn't like that. It's got to be... Okay. Now let's do that again. Keep your eye on the green arrow, which is the magnitude of the velocity. So it almost comes to a stop. Now, I would suspect that an elastic collision, certainly like going through something like branches, as I said, is probably the correct one to use. But if you're talking about like going through a magnetic field with a generator coil or something like that, I think it's an elastic collision again. But what if it was inelastic and all the branches fell off and ended up in the cart or the Ferris wheel or whatever? And we'll make this 3 again and just do the same things. And that's what you see there. You see it slows down a lot. So now let's make this one very small. 0.3. Will it do it? Yeah. No, it won't. And again, keep your eye on the change in initial velocity. That's very slow. Now, we reverse the situation, and there's not much of a change in velocity at all. So as I said, I think the elastic collision is the better model, the better choice here. One thing you can see with like a rotor, if you have a rotor with a north-facing magnet and then it comes across a second north-facing magnetic field, it will bounce off and go the other way. And that's what we saw when you had a small mass going into a large resistance. Whereas with an inelastic collision, that never happens. So it's most likely best modeled by an elastic collision. So how does this explain this? I mean, if it's not clear yet. So let's say we have a pulse motor, and I've made these equal. So this, let's say it's, I don't know, a 1 pound mass, and you give it one push of force that will make it go 10 miles an hour for a duration, and a force that will make the 1 pound go 10 miles an hour. But because of this resistance, it never gets through. And oddly enough, we've seen that if you increase the initial velocity, that same problem remains, because that's just the way it is. So we said this was 1 pound and you gave it a push and it went to 10 miles an hour. So that means if it weighed 10 pounds and you gave it a push, it would go to 1 mile an hour. So it's going to start off 10 times as slow. However, I know that's not 10 times as slow, but just pretend that it is. It gets slower. So instead of the ball or the rotor starting off at 10 miles an hour, it starts off at 1 mile an hour, but it's much more massive. So now it hits the same resistance, and it only loses 10% of its velocity. So now it can rotate all the way around at 0.9 miles an hour, and then it gets a second pulse. And with the second pulse, it will again speed up and only lose 10% of its velocity, and only lose 10% on the third, and on the fourth, and on the fifth. Now eventually you'll start running into more resistance just from the bearings and everything else, but you get the idea. Whereas if you had the small mass, yeah, it's going to take off real quick at first, but when it hits the resistance, it can come entirely to a stop, or it can go, from 10 miles an hour down to 1 mile an hour, so it's not as good. And so it presents a really counterintuitive situation with, for instance, pulsed magnetic motors or any kind of pulsed oscillatory system. As occurred to me after I saw this, the internal combustion engine is a pulsed oscillatory system. You have to pulse the explosion in the piston and then the crankshaft. And so it actually is more closely analogous to a pulsed magnetic motor than it is to the conventional magnetic motor. And this effect then is understood intuitively by society, because you don't use a Toyota Prius or a Toyota what is it, not the Accord, whatever they're called, Corolla, to haul stuff. It's not efficient. You use a big semi-truck, and the semi-tractor trailer has just a crazy amount of momentum as compared to the little Corolla. However, if that same semi stalled out on a train track, it has a tiny amount of momentum, as compared to the train. And so if you want to haul things efficiently on the road, you use a big semi, and it takes a long time to get up to speed, and it takes a long time to slow down. But if you really want to haul things efficiently, you put them on rail, and there it's, and it takes minutes for this thing to get up to speed. And when it does, you better watch your speed, because the momentum that thing has is going to be crazy. Let me try and do something real quick. I want to look at, let me see if I can find this, just the horsepower of a semi. Maybe I'll tell you if I can find it. Not to get too far afield, but I do think that this illustrates the concept as well. So how much horsepower does a semi-truck have? Usually 400 to 600 horsepower. So there are, plenty of performance cars that have 400 to 600 horsepower. It's not probably as much as a Tesla either. And some deliver 605 horsepower. So 500 horsepower. How much weight does 80,000 pounds? That's a lot of weight. Now, does it go any slower than the performance car? Now, the performance car, of course, accelerates more quickly, but they both do 65 miles an hour on the highway, right? So 80,000 pounds, that's 40 tons, if I have that correct. Now, what's the horsepower of a diesel locomotive? 2,000 to 4,500 horsepower. We just said 500 horsepower for a truck, so 4 to 9 times, let's call it 8 times more horsepower. And what's the mass of a train load, if the AI is correct? 3,000 to 18,000 tons. And we just said a truck carries on average 40 tons. So 400, 4,000, 100 times more mass at 4,000. So 100 to 200 times more mass, but the horsepower is only 8 to 10 times greater. So, the horsepower increased eightfold, the mass being moved increased 100 to 200 fold, going from a semi-truck to a locomotive. Does the locomotive go any slower? No. Might even, depending on how good the track is, it might even do, I don't know what it does, but I think it does at least 65 miles an hour. So that's what I'm saying, is that it's kind of understood intuitively by society. So if we look at a definition of work in physics, force acting over a distance. Essentially, if an object moves due to force, then work is being done on that object. So, and force equals, work equals force times distance. So if we go back to the semi and the train, the horsepower increased eightfold going from the semi to the train, but the mass increased 100 to 200 fold. So the train is doing work much more efficiently. With the pulse motor, as we saw a couple videos back, then you get a lot of really counterintuitive behavior then when you add mass, because the thing doesn't accelerate quickly, but because it goes through resistance with a smaller decrease in velocity, its steady state velocity is higher when you add mass, and that's what we saw. And the other point on that was that the resistance we used was a shorted generator coil. And if we go back to the little bit of data that we gathered from that video, you recall when the thing was completely unloaded, it was spinning at 704 RPMs. We put in just an open pickup or generator coil, which had a ferrite core, which caused a little bit of cogging, slowing it down to 668. When we shorted that, it went down to 285. We put in the pennies on the outer part of the rotor. It increased to 778. On the inner part, where they'd have less of an effect on momentum, we saw again an increase, although a lesser one. And the same thing happened loaded. So what I want to look at real quickly, that's not it, equals this divided by that. Come on. And when we added all the pennies, we doubled the mass of the rotor. So when we doubled the mass of the rotor, when it was freewheeling, except for the resistance of the core and the bearings, velocity increased 22.3. Here, when it was loaded, 22.8. And that I suspect is because when it's spinning faster, there's a little more, tiny bit more, if you go really fast, there's a lot more resistance, from the bearings and the thing wanting to wobble and fly apart. But doubling the mass of the rotor, 22%. The thing I'm worried about is the shop class stuff. Because it's one thing to say, well, if a penny flew off, it's going to be going 45 miles an hour. It might even make a little, mark if it hits you. It's another thing if you have a 20-pound rotor that's suddenly galloping across the room at 40 miles an hour. So I want to go at it somewhat slowly, just because you want to try and get an idea of what you can do with 3D printing with the thing not wanting to fall apart. But that's where I'm going with it. Sort of a different video this time, but I hope people enjoyed it. I also found this guy, he's got like 100 different simulations. Like here's a pendulum. I'll show you a cool one. So here's like one of standing waves, and this is on a string, so this would be like a jump rope with a kid here and a kid there, and they're making the jump rope go up and down like that. And there are two things that are cool on this, is then you can, they say, show the longitudinal wave. So there you see the compression and rarefication of the longitudinal waves. And then here, show pressure variation. I thought this was fascinating. Now we can take it out to a full wavelength. Does that look familiar to anyone? That 90-degree offset, that's the exact same as you would see in an LC tank circuit between voltage and current. So just thought that was really interesting, and there's what's going on with the longitudinal waves. Will say I have no idea what any of that means in terms of like anything strange or useful, but just kind of interesting to get a visualization of things like that. So let's end with the conical pendulum. I think I used to just call that tetherball when I was a kid, but now I know it's called a conical pendulum. So I'm ready to throw together the Mark II penny roll, and the only other thing I'm going to do that'll take a little while is I'm going to do bipolar commutation instead of the monopole, and that is just if you're going to do the battery charging thing while you're doing the rest, then you either want to do a cap dump or why not just do bipolar commutation, and that'll get rid of the problem for you as well, if it is a problem. But the strange things that can happen with batteries. Okay, thanks for coming along, and stay healthy, keep smiling. Talk to you later. Bye.